We looked at one example of how a heat wave can be exacerbated by soil moisture feedbacks, and then that affects the planetary boundary layer and the accumulation of heat as well, right? Let's extend that now further to other feedbacks, continuing into wildfire and so on. Roughness length and planetary boundary layer impacts are also critical when we want to look at feedbacks that are important for contemporary climate. They are also important for the past, but to get this kind of data from paleo data is not so easy from paleo proxies. It is clear on evolutionary timescale that as the algae from the ocean colonized land, as best as we know, almost 400 million years ago or so, and they began to grow taller by having hard structures to stand up and compete with others for light, and then eventually releasing pollen and so on. They began to affect the boundary layer, the albedo, and so on. So now that we are in this modern climate with its vegetation biomes, tropical forests, temperate boreal tundras, and so on, we can do the feedbacks that happen in the current context so that we can know what will happen into the future. Okay, so this is another schematic showing the land-atmosphere interactions that combine the biophysical and biogeochemical feedbacks. So this you must keep in mind, that we are looking at biophysical feedbacks where you have vegetation which affects the roughness length and the surface convergence. So if you have upper layer winds away from the surface coming in from, let's say, this direction, and the roughness length is going to affect the frictional slowdown of the winds, which essentially amounts to convergence and can in fact create plenty of convergence of momentum and heat and moisture and so on. But we cannot really separate them also from the associated factors that we will look at in terms of carbon cycle feedback, nitrous oxides, dust, and so on. And you have the impact on evapotranspiration and the microclimate, the scale of which has to be understood yet, as I said. So you have heat uptake, sensible and latent, and then in these regions you have shortwave, reflected shortwave with an albedo alpha, and long wave coming from the atmosphere back to the surface. Remember our energy balance calculations, and the surface is going to emit some long wave as well because it's getting heated up. So there is the evaporative losses and sensible losses, and then the temperature change that's going to create the long wave radiation with the Stefan-Boltzmann law as well. So that gives you a sense. Also, you can see here this figure also includes some snow covered plants, which is going to have a serious albedo impact, which we already looked at. So the amount of heat that goes into the ground, the energy exchange, is going to depend very much on all these sorts of details. We will look at one example of the carbon cycle feedback and vegetation land interactions when we get closer to wildfires, which is a big part of the terrestrial vegetation. Right? This chapter is heavily dominated by land atmosphere interactions because the lead author is an expert in it, and the co-authors are also basically from terrestrial ecosystem, carbon cycle, land atmosphere interactions, and so on. I've added a few ocean things here and there just to make sure that we understand these feedbacks also happen over land. Okay, so the roughness length is then that its vegetation seriously affects it, convergence of momentum, heat, and so on are affected by it. We can now move on to carbon feedbacks. So we'll add ocean as well here. So land and ocean provide a negative feedback to emissions by taking up CO2. This is the concentration carbon feedback we talked about. So we always have to remember the concentration carbon and climate carbon feedbacks, which we can call as biophysical and biogeochemical feedbacks as well. This figure we have seen before, and you've probably seen it many times. Essentially showing from the 1900 into 2019 the amount of CO2 being produced, so it's flux in gigaton carbon per year. The fossil fuel and industry emissions are fairly well constrained. Land use change, deforestation, conversion to agriculture, urbanization, etc., cause some addition to the total emissions as well. So the positive numbers here are emissions into the atmosphere, and the negative numbers are the ones that are drawn down out of the atmosphere. So ocean is obviously taking up some, let's say 25% of the carbon that's being emitted. You can try to do the numbers here. Land is, in terms of carbon fertilization of the vegetation, wetlands, peatlands, etc. So there is a high variability. You can see that the ocean uptake here doesn't show as high a variability as the land uptake does on intraannual timescales. And of course there are trends as well, which is the concentration carbon feedback. As the emissions have gone up, the uptake has also tried to keep up. The question now is whether this will continue or not, whether there will be a limitation on the uptake by land and atmosphere, by land and ocean. Obviously the rest accumulates in the atmosphere, so that's the partitioning of the sinks of CO2, and the accumulation in the atmosphere is what is easily measured in terms of parts per million by volume, because it's a well mixed, long lasting gas that if you measure at a few points in each hemisphere, you get a good measure of the hemispheric CO2 concentration. Obviously that's what we notice most, even though the accumulation in the ocean is doing serious damage with ocean acidification and so on as well. Is there a carbon fertilization happening? There is a recent paper that came out a couple of years ago, which argues, using satellite data over 1982 to 2015, that in fact there has been a change in leaf area. Okay, just if you measure the leaf area without worrying about whether it's agriculture or forest, then there has been a significant increase, especially in let's say China and even India and most of the rest of the world, right? So you can see these yellowish, reddish, purple colors are the loss of leaf area, but most of the world by eye looks like it's gotten greener, at least in terms of a change in leaf area. It turns out that China has done significant afforestation, increase in forest cover, whereas over India, for example, a lot of the increase in leaf area, I think almost 80% or more, comes actually from agriculture. So then the critical question is whether the carbon climate feedbacks and the concentration carbon feedbacks result in agriculture also taking up more carbon. So we have seen in many places enhancing land sink of carbon, and it comes down to reducing the emissions from agricultural land with practices like no tillage, avoiding excess irrigation and so on, and using cover crops, etc., to also improve soil carbon and loss of soil erosion and so on and so forth, soil moisture persistence, etc. Okay, so there is some evidence of carbon fertilization, then the question is whether this will continue as well with warming and with precipitation changes and extremes and so on, and ozone increase. There is plenty of evidence that actually crop yields are going to go down. Okay, so we have to be careful about interpreting short time scale increases in leaf area. So we will need models for projections that can capture many of these feedbacks that I mentioned between leaf area index, concentration carbon, and climate carbon feedbacks. So we'll look at other details as we go along.